Welcome everyone. Today we're going to decode the technology stack behind YouTube, the world's largest video platform. We'll explore how YouTube manages to serve billions of users, process massive video uploads, and deliver smooth streaming experiences globally. By the end, you'll have a clear picture of the architecture, the challenges, and the innovations behind YouTube. First, we look at the YouTube's architecture. You can either have a mobile client or a web client. That is, you can either access it through an app or through the website itself, both of which you'll be able to watch the video. And the first thing that will happen is that your video watching request will go to the load balancer and then go to the web server where it will go to the media cache or the media storage where the video is processed. And then there is also something else like the processing queue where the thumbnails are stored and the metadata is stored and the user data is stored. That happens on the backend. If you're trying to upload a video, the process is similar, but there's some changes where the video that you're uploading will also go to the load balancer as a request and then go to the web server. And the parts of the video that you've uploaded will be stored in different places. That is, will be stored in the media cache or in the media storage, and the thumbnail will be stored in the thumbnail storage. And then all the other metadata caches will be stored in the cache part of the ecosystem. So then we'll be looking at how clients function. The devices and platforms where users interact with YouTube are called clients. So then we'll have mobile clients and web clients. YouTube is accessed from smartphones, tablets, desktops, smart TVs, and even gaming consoles. Supporting this diversity is a huge engineering challenge. So then there are only two primary options that the user can do. That is either you will be watching new videos or be uploading new content. Each generates requests that must be efficiently routed and processed robustly. Fun fact. YouTube has over 2 billion logged in monthly users, and more than 70% of the watch time happens on mobile devices. And then we'll come to load balancers and web servers. When you click play or upload a video, your request first hits the load balancer. Load balancer. Think of this as a traffic cop, directing millions of requests per second to the right web service. This ensures no server gets overwhelmed, which is crucial for reliability and scalability. Then we'll come to web servers. These servers handle user authentication. They will manage uploads and coordinate with backend services. They are the main entry point for all application logic. Imagine a huge airport with multiple terminals. The load balancer is like air traffic control, ensuring every flight lands at the right gate. That is basically, let's say, for example, I'll bring an example to you. You are seeing the IPL. The IPL is a local tournament that happens in India. That is, other country people will most probably not be handling. They'll not be trying to see IPL videos, right? So when you're trying to access an IPL video, what will happen is that a lot of IPL video requests will come in from a single place. If they have servers that only correspond to a single place, then this is going to fail because a lot of requests come at the same time and the load is not balanced and the servers will crash. So what YouTube does is it has its load balancer. That is, when you raise a request, it will evenly distribute incoming requests, even if it's watch or upload, across multiple web servers such that no single server will get overloaded, which will improve reliability and scalability. And then the web server is kind of like an admin where it will handle user requests, authenticate user, and it will do all of the main logic that is required for YouTube to function. Then we will come to processing queues, transcoding servers, and media storage. So then processing queues. When you upload a video, it's first placed in a queue. This decouples the upload process from video processing, allowing YouTube to handle uploads asynchronously and at scale. What asynchronously basically means is that it doesn't go one by one, but rather it happens in parallel. That is, if three videos are uploaded, one right after the other, YouTube doesn't wait for your video to process and then it doesn't go to the next and it doesn't go to the next. Like what happens in a stack. The processing happens in parallel such that your video, the next video, the video after that are all processed asynchronously, that is parallelly. They're all processed at the same time. Then we'll come to transcoding servers. Videos are converted into multiple formats and resolutions. This is called transcoding and enables adaptive streaming. So whether you're on a slow 3G connection or fast fiber, you get the best possible quality. So whenever you're trying to access YouTube videos, then you'll see these things called Ultra 4K HD or 4K or 1080 pixel resolution or 720 pixel or 360 pixel or 240 pixels. So what YouTube does is when someone uploads a video, these videos are converted into multiple formats and resolutions. That is, they're either or converted to formats that fit into mobile devices or only into for tablets or for laptops. And so all of these multiple formats are converted, and then also the resolutions are stored separately such that it will ensure compatibility across different devices and will enable adaptive streaming. That is, at any time, depending on your data quality, the YouTube video's resolution will be switched. Then we'll come to media storage. So then both original and processed videos are stored in highly durable, scalable object storage systems such as Google Cloud Storage. These systems ensure videos are safe, redundant, and accessible from anywhere in the world. What's that for you? Over 500 hours of video are uploaded to YouTube every single minute. And then we were talking about data compression and transcoding service. I will explain how that also works to you. YouTube uses advanced codecs like VP9 and H264 to compress videos, reducing storage and bandwidth needs while also maintaining quality of the videos. And then there is resource intensity. Newer codecs like VP9 offer better quality but require up to 5 times more compute power to encode than older codecs, which basically means for a billion users and almost million videos uploaded altogether, then 5 times cost is going to make YouTube go broke, basically. So what YouTube does is it still sticks to advanced codecs H264 for most of the videos, and only for the videos that require VP9 will it actually convert it to VP9. And that is why when you're trying to access these very high resolution videos, that it'll ask for you to have a premium account for YouTube to actually afford to convert that into that specific format that you require. And then we'll come to CDNs, media caches, and thumbnail storage, content delivery networks. CDNs. So CDNs cache and deliver popular videos from servers near users, reducing bufferages and load times. YouTube leverages Google's global CDN infrastructure for this. Then we'll come to media cache. Frequently accessed videos and images are stored in a media cache to further reduce latency and speed up access to trending content. Thumbnail storage. Thumbnails are accessed constantly for previews. By storing them separately in optimized storage, YouTube ensures instant preview loading. As an analogy, think of the CDNs as a network of local grocery stores. Instead of everyone going to a central warehouse, you get your items from the nearest store, which is much faster. That is basically what caching is, that all of your data is usually stored in the CPU. And for some data to be accessed from the CPU, it is extremely hard because it takes a lot of latency, that is time, for your request to go to the CPU and then to get processed from the CPU and back to you. So what media caches will do is that these temporarily store the data on RAM itself. But what the problem that you'll face with caching these information is such that this is not very durable or maintainable. That is, if for some unknown reason your CPU crashes, then some of the data is not going to be stored there. But for that trade-off, what you'll get is it'll reduce latency. That is, the process times are very less, and it speeds up access to popular content such that you are not kept waiting at all times. And it's a similar process to content delivery, where the data is stored in servers that are closer to you. That is, if you are in India and you're trying to access a video, the video that you're trying to access will come to you from India itself, such that the buffering time and the loading time from the content is minimized, and then you will also be able to see the video much quickly and much more easily for you. And then for thumbnail storage. So thumbnails are the most important part of a YouTube video because that is what intrigues you to go and look into a YouTube video, right? So when only if you're attracted by the thumbnail will you be able to click on the video, and so that's why thumbnails are given special preference and they're stored at a separate location so that it has optimized storage and you can see the thumbnail quickly and you can click on the video based on the thumbnail itself. And then we will come to application servers, user databases, and metadata databases. So then we'll come, these are backend services. Application servers. These handle business logic, recommendation, analytics, and user management. By separating these functions, YouTube achieves better scalability and reliability. Then we'll come to user database. It stores user info, preferences, and history, enabling personalized experiences and account management. Then we'll come to metadata databases. These stores video data, metadata like titles, description, tags, view counts, comments, and more. Fast search and retrieval are essential for features like these because this will help you find recommendations and trending videos. A specific design note. YouTube uses a mix of structured query language SQLs and NoSQL for high throughput analytics and interactions. So then, if you're ever wondering that how is YouTube able to suggest a video to you that is relevant to you and yet you're not actually signed into YouTube. For example, you're signing into YouTube as a new user and hence you don't have any preferences that you've actually mentioned to YouTube and YouTube doesn't have a database on what you like. So then what it does is it goes and looks at users near you in the same country or in the same region and in the same age group as you, and then it'll recommend videos that these people are regularly watching. And after some point of time, when you're watching all of these YouTube videos, it'll store all of your user information, preferences, and history, and then it'll use machine learning or artificial intelligence algorithms to then process all of these data, and then it'll figure out what kind of videos it can suggest you next, so that user engagement is also at a all-time high, and then the advertisements that it suggests to you are also relevant to you, such that you're also engaging with the advertisement, and YouTube can make money off of that as well. And then we'll come to metadata cache and how the data flow works. So then we'll come to fast access and data flow. Metadata cache. Frequently accessed metadata is cached to reduce database load and speed up access to popular video information. And then for watching a video, the flow is client request to load. A client will raise a request that will go to the load balancer, and then the load balancer will send the request to the web server, which will go to the media cache or the CDN or the metadata, media storage, metadata cache, database, thumbnail storage, and so on. And then all of these will be retrieved, and then based on the authenticity of your request, the request will be verified, and all of these details and the video that you have been requesting will come straight to you. And then we'll come to video uploading. The flow is such that the client will upload a video, it will go to a load balancer, it will go to the web process server, and then it will go to the processing queue. Then the transcoding servers will transcode off the data that you've given it, that is to convert all the formats and the pixel values, and then it will go be stored in the media storage and then into the CDN or the cache. Basically, caching is like keeping your favorite snack in the fridge, so you don't have to run to the store every time you want to grab a bite. Then we will be discussing front-end stack. The front-end stack for YouTube is basically Angular, React, Preact, HTML5, JavaScript, TypeScript, and in Android it's Kotlin and Java. For iOS it's Swift. Hybrid SSR and SPA. Server-side rendering ensures fast initial loads and SEO, while single-page application SPA architecture allows smooth interactive navigation without reloads. So then YouTube uses Angular, which is Google's own development. That is, it was developed by YouTube for YouTube by Google. And then it'll use React and Preact for dynamic component-based user interfaces. HTML5 enables JavaScript enables plugin-free video playback, and JavaScript and TypeScript power interactivity. Preact is used in high-traffic areas for lightweight performance. And for iOS, it was developed using Swift for native integration and performance, and for Android, Java and Kotlin are used for a robust, efficient, and compatible with Android ecosystem. Then we'll come to the backend stack. So the backend consists of three main aspects, which is microservices, communication, and orchestration. For microservices, Java, Go, Python, and C++ are used. For communication, REST, gRPC, WebSockets are used. And for orchestration, Kubernetes, Borg, and Spinnaker are used. And why are these specific services used is that each service is isolated for independent scaling and reliability. Java powers core infrastructure, Go and C++ are used for performance critical services, Python for scripting and automation. For communication, REST for standard client server APIs. Basically, how client servers work is that a client will raise a request, and that request will be verified using an API, And then that if that request is verified, then the server based on the client's request will give you a specific answer. Then gRPC is used for high-speed, efficient internal service communication. And as for WebSockets, they are used for real-time features like live chat and live streaming. And then for automated deployment, scaling and management of containers and services for global reliability is given by Kubernetes and Spinnaker. So then why are we using this is because of the design principle. Microservices allow YouTube to deploy updates without downtime and scale services independently. For example, YouTube is only developing on its some aspects of YouTube that is only on the video accessing part, then it can only develop that part and leave the rest of the packets alone. But if you're developing everything together as a monolith, then everything will have to be fixed all together, and each of it has to be changed accordingly to what update you're making for that single specific microservice inside that monolith. But for a microservice, you can make all of your changes independently and they're isolated, and so they don't cause dependency clashes. Then we'll come to data storage and processing. Video storage. YouTube uses object storage like Google Stock Storage. For metadata, it uses Bigtable and Spanner. For caching, it will use Redis, Memcached, and CDN Edge. And for event, it will use Apache Kafka and Google Pub/Sub. So why is this used? Object storage is optimized for massive video files, durability, and scalability. For metadata, Bigtable NoSQL uses stores user interactions and analytics for high throughput and low latency. And Spanner, which is used for SQL, handles structured data and transactions with global consistency. For caching, Redis and Memcached cache hot metadata and content for low latency access. For event streaming, Apache Kafka and Google Pub/Sub enable real-time analytics, messaging, and data flow between distributed systems. Redundancy. Videos are stored in multiple data centers around the world, ensuring safety and accessibility even if one center goes down. So why has Google chosen these specific features for YouTube? Angular and React are dynamic scalable UIs. Native mobile integration for Swift and Kotlin ensure that the best performance and integration for that specific website or app. And then for the backend, microservices allow for independent scaling and reliability. Using multiple languages, that's YouTube optimized for both performance and developer productivity. For storage and processing, object storage, distributed databases, and caching ensure durability, speed, and scalability. Google's own CDN offers deep integration, cost effectiveness, and unmatched performance at global scale. And some challenges and innovations that Google faced are that for 500 plus hours of YouTube videos are uploaded every day per minute. So then there's billions of daily views. And then there should be no buffering, which is it has to ensure high availability and minimum latency even during viral spikes. And there should be no buffering. And then there should be adaptive streaming, that is, it has to support multiple formats and resolutions for seamless playback on any device or network. And then for content moderation. Content moderation combines AI algorithms and human reviews to filter inappropriate content. Analytics and monetization. It provides real-time analytics and monetization tools for millions of creators. Innovations. So new codecs like VP9 and AV1 for better compression quality, but at a higher computer cost. Edge computing, serving static content from CDN to CDN edge nodes closer to users for lower latency. For real user monitoring, it tracks real-time user experience to quickly address performance issues. And so we look at some more things that have made YouTube the monolith that it is today. So the API gateway and security API gateway role. Before requests reach backend services, they often pass through an API gateway. This centralizes authentication, rate limiting, and routing, protecting backend systems from abuse and simplifying version management. For example, if someone has a bot, for example, that wants to scrape data from YouTube, that means this bot is going to click at YouTube videos much quicker than what a human would click. That is, for example, if you're clicking at most, let's say, 2 or 3 videos per second, the bot will be able to click 20 to 30 videos, which means it will raise a lot of requests that will end up causing the servers to crash because of so many requests at the same time. Then that is why YouTube uses rate limiting. That is, it will limit the rate of request that a specific person or a bot can make at a specific time, hence causing the bot to make lesser requests and freeing the space for YouTube servers to work freely. Then there are security layers. YouTube employs OAuth for secure user authentication, HTTPS for the encrypted data transfer, and DDoS protection to prevent service outages. What OAuth basically does is that when you're logging into YouTube, if you click on the sign in button, it will say select a Google account for you to log in with. This is basically how OAuth works, where you will click on the user email that you want to log into. And then once that is selected, YouTube will reroute you to the OAuth portal using which your validation or your security will be verified, and then you will be able to log into YouTube. Then it'll have direct storage uploads and signed URLs. When uploading, YouTube generates a signed URL, allowing users to upload directly to object storage without routing large files through the main app servers. This offload traffic and increases scalability. Once the upload completes, the client notifies YouTube, triggering transcoding and metadata processing. While this says client notifies YouTube, that is not client from your part. Once the video is done uploading, from the client side itself, YouTube will be able to trigger the transcoding and metadata processing. And dynamic adaptive streaming over HTTP dash. YouTube sets videos into small segments at multiple bit rates. The player requests the best segment based on real-time bandwidth, ensuring smooth playback even if network conditions change. For example, if you're watching a YouTube using your Wi-Fi and you're able to get 720 pixels, and then suddenly the quality changes to 144 pixels because you've switched to your mobile data, this is basically how it's working. That is, because your network was good then, YouTube is splitting the video for 720 pixels till your network was good. Once the network is not good, at multiple bit rates, it will be switching to the lesser pixel value so that it's easier for your network to handle whatever YouTube is providing you. Then HLS and RTMP. For live streaming, YouTube uses protocols like HLS, HTTP live streaming, and RTMP, real-time messaging protocol, to deliver content with minimal delay. And then for codec evolution, YouTube supports VP9 H264 and is adopting AV mode for better compression quality, especially important for 4K and 8K and mobile viewers. And edge computing. YouTube's content delivery network not only caches videos, but can directly run edge functions such as serving personalized recommendations or ads directly from edge nodes, reducing backend load and latency. Geo-replication. Videos are replicated across global data centers, ensuring users everywhere get fast access and the system can withstand regional outages. And this, for example, for a content creator in the United States, and you're trying to see a video from India, in normal cases, if there's only one specific copy of that video that is available and that is only available in the United States because that is where the user has uploaded their data, so their video. Then for your network to communicate with the network that has the video there will take a lot of time and hence that will create latency and you will have a laggy feeling or your video will keep loading for lot of time. So what happens is that videos are replicated across global data centers, that is across all countries, and in the data centers that YouTube has, these videos will be replicated such that instead of your network routing to the United States for them to access the video, it will be accessed from the region that you're already available at. And hybrid SSR and SPA. As we were talking about earlier, server-side rendering delivers fast initial loads and SEO benefits, while single-page application architectures enable smooth navigation without reloads. In high-traffic areas, YouTube uses Preact to reduce JavaScript bundle size, improving load times on slower devices. Service workers. These enable offline access to cached assets and speed up repeated visits by storing static files locally. Real-time user monitoring, RUM. YouTube tracks real user performance metrics, allowing engineers to quickly identify and fix front-end issues. And recommendation engines. YouTube's recommendation system uses TensorFlow and PyTorch to analyze user behavior, watch history, engagement, delivering highly personalized video suggestions. A and B testings. YouTube constantly runs experiments on UI and algorithm changes using real-time data to optimize user engagement. And for real-time ingestion. Live streams are ingested, encoded, and distributed globally with minimal latency. Adaptive bitrate streaming ensures viewers with different network speeds get the best quality possible. WebSockets for live chat. Real-time chat and notifications during live streams use WebSocket, enabling instant updates without constant polling. Infrastructure can instantly handle up to millions of concurrent live viewers using Kubernetes and Borg for orchestration. And then, as we were talking earlier, big table NoSQL stores massive volumes of user interactions while Scala SQL handles transaction structured data both designed for global scale. That is for volumes of user data that require low latency and quick access, NoSQL is used. And for data that requires safety and security but does not require the time for SQL to go and access that data, can be handled by Spanner. Real-time analytics. Apache Kafka and Google Pubsub stream billions of events per day, powering dashboards for creators and advertisers. Redis and Memcached provide fast access to trending video metadata, reducing database load. Global redundancy. All critical data is replicated across multiple data centers for disaster recovery and high availability. Tools like Spinnaker and Kubernetes allow YouTube to deploy updates with zero downtime even during peak traffic. Tag driver and custom dashboards track system health, latency, and error rates in real time, enabling rapid response to issues. Content system. This supports real-time updates, threading, moderation, and spam filtering using both automated and human review. As we were talking about earlier, machine learning algorithms are built for the YouTube to monitor what kind of comments are being sent into the chat. And then that is also sent for human review, such that the humans will be reviewing this, and then they can either moderate or remove whatever comments that have been put on the YouTube that does not align with their terms and agreements. So push notifications keep users engaged with new uploads, live streams, and community posts. Localization. YouTube supports dozens of languages and regional content policies, adapting UI and recommendation per user languages. React Server components. Potential for even smoother SVA transmission with less JavaScript sent to the browser. WebAssembly, WASM. This could enable in-browser video editing or processing, offloading work from servers. Edge AI. Running a recommendation or moderation models at this alien edge for faster, more personal experience. Responsive design. YouTube ensures a constant experience across devices and screen sizes. Accessibility. Auto-generated captions. Keyboard navigation and screen reader support make YouTube usable for everyone. And where is the future of YouTube going? YouTube continues to explore new technologies like edge computing, service mesh, example Istio, and GraphQL APIs for even more efficient data delivery and personalization. The platform is experimenting with real-time recommendations powered by streaming data and Kafka, aiming to make suggestions even more relevant and timely. With the rise of 8K video, VR, and interactive content, YouTube's architecture is being pushed to new limits, driving innovation further in video delivery and user engagement. Now that we've discussed the future of YouTube, we will see how a specific workflow of a singular video works. First, capture and upload. A user records a video, uploads it to YouTube via its web or mobile app. The upload passes through a load balancer, then a web server for authentication and validation, and then the processing queue and transcoding. Video enters a processing queue for asynchronous handling. Transcoding servers convert the video into multiple formats and resolutions for compatibility and adaptive streaming. Storage and CDN. Both original and process files are stored in object storage, that is in Google's cloud storage. Files are distributed to CDN edge nodes for fast global delivery. And then in playback. When a user requests to watch the video is served from the nearest CDN or cache for low latency. Then the metadata, that is the title, description, comments, are fetched from the databases and thumbnails from optimized storage. User interaction and analytics. Users can like, comment, share, and subscribe, and the analytics are tracked and stored for the creators to make later changes if required. And then we look at the workflow of a live stream. The live stream has to capture and have real-time encoding. The creator uses a camera or a mic and a streaming encoder to capture and encode live audio and video. Encoder compresses and formats the stream for efficient transmission, and for the ingestion, encoded streams are sent to YouTube's ingest server using RTMP or HLS protocols. Stream process to a load balancer for distribution. And for real-time transcoding, YouTube transfers the live stream into multiple resolutions and bitrates on the fly, enabling adaptive bitrate streaming for all viewers. CDN distribution. Live stream segments are distributed to CDN edge locations worldwide, minimizing latency and buffering. For playback and interaction, viewers receive the stream in real time from the nearest CDN node. Live chat and real-time viewer counts are enabled, allowing direct interaction between creator and audience. Adaptive streaming ensures smooth playback regardless of network speed. And as for metadata and analytics, metadata assists the title, description, privacy settings is managed in real time. Live analytics are tracked and displayed to the creator. And that is if you're putting a comment on YouTube in a live stream, the creator is able to see it in real time as you've sent the message to them. And recording and post live processing. The live broadcast can be recorded and saved as a regular YouTube video for replay. After the stream, the recording may be further processed, that is using additional encoding and thumbnail generation and published for on-demand viewing. Thank you for coming to the stream. And today we discussed how YouTube works and why it's such a massive software that a lot of people are using at all the times and why it is the number one uh, service provider for live streaming videos or for uploading and accessing videos. And I hope it was an interaction session. And if you guys have any doubts, please feel free to post it in the chat box. Thank you.